So I've got my division statement here. And if my remainder is 0, notice what happens. Well, that really, I can just kind of get rid of that. And what ends up happening is this divisor and the quotient end up being factors of this polynomial. So when we divide and we get a remainder of 0, the divisor is a factor. Okay, not only is the divisor the factor, in fact, we should actually even add on to here, the quotient is also a factor. Okay, the quotient is a factor as well. So if I use my remainder theorem with this property here, if I use my remainder theorem and divide by x minus a, and I plug in a, and I end up with 0, that means it divided evenly, there's no remainder, which then leads me to conclude that x minus a must be a factor of that polynomial. So we can use this factor property in remainder theorem to determine the factor. So what I can do is I can just plug in some potential factors. Now, that poses a little bit of a problem in that what can I plug in here? Well, I could plug, 15 maybe, but 15 doesn't seem reasonable. What would seem reasonable is if I could understand how some of these terms are generated, in particular this last term, I can probably have reasonable guesses. Instead of just random guesses, I can use some reasonable guesses. And what is a reasonable guess all the time is the fact that 1 is a divisor for anything. So we could have an x plus 1 or x minus 1 factor, and that could be a potential factor for almost any polynomial. So I'm going to do this. I'm going to say test p of 1. Okay, so I'm going to say p of 1 is equal to 1 plus 4 minus 1 minus 16 minus 12. Okay, and I don't even care what it's equal to. I just need to know, is it 0 or not? And that one's clearly not 0. And then I could test another easy number, negative 1. And I end up with 1 minus 4 minus 1. This ends up being plus 16 minus 12. Now in this case, if I add this up, I get negative 17 plus 17. Well, this one is equal to 0. Okay, and this is key because if this is equal to 0, that means that's the remainder of 0. And that means that the factor x plus 1 must be a factor. And remember that we said that really that's kind of what we're interested in. We want to know factors. So that must be a factor. Okay? And so I know that if I were to factor this, x plus 1 is one of the factors. I could try, p of 2. And I can plug 2 in. 2 to the power 4 is 16, plus 8 times 4 is 32, minus 4, minus 32, minus 12. And what's that equal to? Well, this one happens to, these ones cancel out. Negative 16 and positive, that one's also equal to 0. Well, if it's equal to 0, I know that that must be a factor. So I know this is a degree 4 polynomial, so I know it has 4 factors, and I've already established 2 of these factors. In fact, I can find all of my factors this way. Okay? I can find all 4 of my factors this way. However, this is highly inefficient, so we may want to have some other strategy in addition to this, but this at least helps me find some factors. I'm going to maybe try another one. Try my luck here. Negative 2. Okay? If I plug negative 2 in here, I get 16. I get minus 32. I get minus 4. This one becomes plus 32. Minus 12. This one also equals 0. Okay, so I end up with x plus 2. It must be another factor. So I've got 3 factors already. I must be really good at this. Okay, and so I just need one more. In fact, I can kind of guess what that last one is because I know that these factors multiplied together. So I'm just going to write it out. X x plus 1, x minus 2, x plus 2. When I multiply the last numbers together, 1 times 2 times 2, negative 2 times 2, I get negative 4. I need to get negative 12, so I know that the next factor must be plus 3 to get the other, to be able to get that negative 12 factor at the end. Okay, so now I've actually gone from an expanded fourth degree polynomial, and somehow I've managed to put it into factored form, which is really useful because now I can find zeros, I can find roots, I can do lots of things. Okay, and I'm just going to test that last one. I'm pretty sure it's correct, so I'm just going to just plug it in just to make sure. Test my remainder theorem. So I end up with 81 plus or minus, that's going to be 27 times 4, that's 108, minus 9 plus 48 minus 12, and I'm going to get here, looks like negative 117, negative 129, positive 129, yeah, that's equal to 0. So now I've got all 4 of my factors. Okay, now I kind of had to guess at these, and you know, if I were to, I was kind of got lucky because I got all 4 in a row. But yeah, this is, although it can be done this way, you can see definitely there's some holes in this strategy. So we want to try to have some other strategies to do this. And the other strategy is, well, first of all, we don't want to randomly guess. So that's going to be the first thing. Instead of randomly guessing, how can I keep my guesses appropriate? And one of the ways is that, well, I looked at that minus 12, and I know those last numbers must multiply to minus 12. So if I'm going to do any guessing, I'm going to do factors of 12. So same thing here. If this is 48 here, I need to be able to have brackets. So I'm going to, in this case, have 3 brackets like this. Okay, and it's going to be x times x times x to give me an x cubed. But I know that these numbers here, which end up being my guesses for my remainder theorem, those numbers there must multiply to, and I'm just going to hide 48. Okay, so what I'm going to do is I'm going to look for factors of 48. So what are some factors of 48? What divides into 48? Well, plus minus 1, plus minus 2, plus minus 3, plus, there's lots here, 4, plus minus 6, plus minus 8, plus minus 12, plus minus 16 even. Okay, there's quite a few, so this is getting a bit onerous, but we know there's only 3, and I don't have to test these really big ones. In fact, I probably want to start with the smaller ones because these are unlikely. So I have like a few numbers here, at least I can start with. And this is the starting process of how I can start factoring. I can use this remainder theorem to at least guess one factor. Okay, and I'm not going to randomly guess. I've got some limited guessing that I can work on. In fact, although this has lots of possibilities, I'm probably just going to stick with the first few because in the end, I'm going to show you that we only need one.